In this video, we're going to look at a few other transformations that can occur. So through two examples, we're going to look at reciprocal transformations where you start with an original function and then just take its reciprocal. Then we're going to look at some changes from the modulus function that can occur in a graph, and you'll learn a little bit of extra programming in GeoGebra that's fairly simple and straightforward, but it's hard to know if you don't know. So to start with, I've already put in these graphs, so we're going to look at the linear case. That's y equals x minus 2, as you can judge from the intercepts, I'm sure. And this one is the reciprocal of y equals x minus 2, so y equals 1 over x minus 2. Now, you see 2 points here where they intersect. Those are called invariant points because they don't change location when you go from one graph to the other. They stay in the same spot, those 2 points. You can guess where they're going to be by looking at the function that you're going to take the reciprocal of and then considering that you're taking the reciprocal. So a value that doesn't change is of course going to be equivalent to 1 over 1, okay, for reciprocal. You can also judge what's going to happen with the graph if you look back and you remember that a graph like 1 over x minus 2 is a simple rational function, so we can imagine that it came from 1 over x and we can see where it's going to move. Another thing we can do with any reciprocal graph is we can look at where the original graph, which is this line, was 0, so it was 0 at x equals 2. At that location, when we take the reciprocal of 0, it's going to shoot off to infinity. Where we're a little bit higher than the 2, it's going to go to positive infinity because you're dividing by positive 0, and negative infinity here because you're dividing by something very close to 0 on the negative side. Okay. Where the original function goes off to plus or minus infinity, the reciprocal function is going to go off to 0, of course, because if we divide by infinity, we get 0. So we can very quickly sketch these types of graphs, even without GeoGebra. I'm going to take these off the screen, and we can see the same sort of thing with the parabola. This is y equals x squared, and then if we change that to its reciprocal, 1 over x squared, we get this. We get 2 invariant points, which again are very predictable in very predictable locations because we have a graph that's being squared, so here's a 1, here's a minus 1 squared is still 1, so it doesn't change, and then we take the reciprocal. Okay, so we look at the invariant points to see where we're going to have a crossing, and then we look at the infinities and the zeros. So it was 0 here, the parabola was at the origin, so the other graph's going to go off to infinity. And where the parabola is going to infinity, the reciprocal is going to go to 0. Now, for the modulus function, if I start with a function like this one, which is y equals 3x squared minus 6x, if I want to take the absolute value of that, the whole thing, the entire function, then it will look like this. And you see now there's a bump in the middle. If I make the original one hidden, then you can see that actually these arms here on the side are part of the absolute value graph as well. That should be expected because these were already positive values. So when you take the absolute value, positive values remain the same, unchanged. But anything that was negative, like the bottom part of the parabola, is going to become positive. So it gets flipped up, essentially, reflected across the x-axis. That's if you take the absolute value of the entire function. If I instead start with this graph, and then I take the absolute value not of the whole function, but only of x. So I have f as a function, f of x changes to f of the absolute value of x. Then now if I do that instead, it's going to look like this. So you see I've taken the original off the screen, and this is what we get instead. Original adds in this line right here. So this was the original that I'm tracing. What happened when we did the absolute value of x is that this part of the line disappeared, and then we got this bump. Okay. So why might that occur? Well, when you take the absolute value of x, what's happening, take off the original, is that if you can look in close on this formula that I have here, you can understand as well. If x is greater than 0 or equal to 0, then we go with a positive value for x. We just leave it as itself because it was already positive. So we just leave it as positive. So it's still 3x squared minus 6x where my cursor is. However, if x is not greater than or equal to 0, if it's actually less than 0, we know we're going to put a negative sign in front of the x, because if it's negative, we're going to make it positive for the absolute value sign, so we put a negative on. If I put a negative on x for x squared, it's not going to change anything, because negative x squared is still x squared. If I put a negative on the x from the negative 6x, it's going to be negative 6 times negative x, which is a positive 6x. So for my second condition, I've changed to 3x squared plus 6x. What this if statement does is says if x is greater than 0, display the original graph, 3x squared minus 6x. If it's not greater than 0, means it's less than 0, display 3x squared plus 6x. I am being a little bit loose in my greater than or equal to symbol here, because the graph is continuous at 0. I don't have to really worry about it. There's no gap. But I should probably have greater than or equal to 0 here to be absolutely sure if I didn't already know that. So if x is greater than 0, original graph. If x is not greater than 0, be a modified graph, which we get from our understanding of the definition of the absolute value. So the if statement shows the condition, what to show if the condition is true, and then after a comma, what to show if the condition is false.